All right, so today we're going to talk about parallelograms.
Welcome to Mr. Baker's House of Knowledge.
So, thank you for that.
No, I was so excited I missed it.
So, a parallelogram is a quadrilateral. So, what's a quadrilateral?
4 sides.
It's a four-sided polygon. A parallelogram is even more specific. It has 4 sides, but both pairs of its opposite sides are parallel. That is the definition of a parallelogram. So it's important to understand a few terms. Opposite sides, to me this is common sense. Opposite sides are sides that don't touch. And then we've got something called opposite angles. Opposite angles are angles that don't touch. Now, you can get a little bit more technical about that. You can say that opposite sides don't share a vertex and opposite angles don't share a side. But, I mean, does anybody have any confusion about what an opposite side is and what an opposite angle is in a four-sided figure? All right, we're going to learn some truths about parallelograms today. And then later we're going to turn all of those truths around, and they're going to be the ways that we prove that something is a parallelogram. You might be surprised to learn that there are 5 ways to prove that a quadrilateral is a parallelogram. Like I said, this class is the class of ways. Oh, you're so excited about the extra credit. So, you can abbreviate parallelogram with the little parallelogram symbol. And if you want to talk about the plurals of parallelograms, you can put a little S in the parallelogram symbol, and that makes it plural. All right, so let's talk about something, and we're actually going to go through and do proofs on these things. So this is pretty much the last unit that we do a lot of proofs in, but it's very proof-focused, so you need to keep going with your note cards. So we're going to prove that if something is a parallelogram, then that automatically means that both pairs of its opposite sides, the sides that don't touch, will also be congruent. So they'll be the same length. Here's how we go about doing that. So first of all, if I claim that something is a parallelogram, like I have down here, I'm claiming parallelogram ABCD. That's what kind of information? That's right, given. Everybody should get the givens. Now, if it's a parallelogram, then what that means is, by definition, the opposite sides, in this case A, B, and C, D, B, C, and D, A, are going to be parallel. So what I think I'm going to do is I think I'm going to take a little picture of the figure, and I'm going to make it a little bit bigger so we can mark on it. Can you see me now?
Yes.
All right. So what I've said so far is that BC is parallel to AD and AB is parallel to CD. And that is by the definition of a parallelogram. Yes, ma'am, you are correct. All right. Now, if you kind of extend some stuff out, whoa, that's way bigger of a highlighting than I wanted to do. Let's see if I can trim that down a little bit. Let's try that. So if you extend this out, you should see that AC is a transversal and BA and CD are one groups of parallel sides and BC and AD are other groups of parallel sides. So what this is telling me is that angle 1 and angle 4 are congruent because they're alternate interior angles of the yellow lines cut by the purple transversal. And also, angle 2 and angle 3 are going to be congruent because they are alternate interior angles of the green lines cut by the purple transversal. So I can say that angle 1 is congruent to angle 4. So angle 1 congruent to angle 4. And angle 2 congruent to angle 3 because alt, int, angles congruent if lines parallel. Do y'all remember that one?
Yes, sir.
If you don't, it's time to dig back out those note cards. How many people have actually made note cards and still look through them? We kind of got a half-hearted from one person, and then a lot of people made them, but then they fed them to their dog or something.
My brain's a big no.
Yeah, or some people have big brains. All right, big brain. Why is AC congruent to AC?
CPCT. Oh, reflexive.
Yes. Big brain needed a little bit of a jump start
I
there.
had to shuffle through my note cards for a little bit.
At least you didn't say reflective.
I would never.
Why then would triangle ABC be congruent to triangle CDA?
Angle, side angle.
Angle, side angle. And then now, once the two triangles are congruent, why are BC and AD congruent and BA and CD congruent? CP, CT, C. So there you go. That's an application of using proofs to prove a brand new theorem. And our theorem is, if something is a parallelogram, then its opposite sides are congruent. So you can now use that as a reason in your proofs, because we've proven that to be true. So don't say theorem 6.1, say, if it's a parallelogram, then opposite sides are congruent. Or opposite sides are congruent in a parallelogram. So there's this other thing about parallelograms called consecutive angles. To me, this is almost a not needed theorem because it's the same thing as two supplementary angles on parallel lines cut by a transversal being supplementary. I'm sorry, two same side interior angles being supplementary if you have two parallel lines cut by a transversal. But we're going to say it for parallelograms too. So if something's a parallelogram, then consecutive angles will be supplementary. So the B and C would be supplementary. C and D would be supplementary. D and A would be supplementary. A and B would be supplementary. If you're not familiar with the current term consecutive angles are angles that share a side. So angle B and angle C both share side BC as one of their sides. That makes them consecutive. That makes them supplementary. So the proof to that, I'm not even going to go through the proof on that, because the proof on that is the same as the proof we would use to prove same side interior angles are supplementary. It's almost the same thing. All right, so we could get problems involving consecutive angles. What would be the measure of angle P in this drawing? Well, we know that PQRS is a parallelogram. So the measure of angle P plus any consecutive angle, and in this case, a consecutive angle is angle S, would equal 180 because they're supplementary. So the measure of angle P plus 64 would equal 180. And so we just subtract 64 from both sides, and we get 116. So what's the solution? C, 116. So do you see how we use consecutive angles to solve problems?
Yep.
So we're going to have situations where we're solving problems, and we're going to have situations where we're proving things. And there's more rules than what we're going to cover today. Today I'm just picking a couple of them. Finally, the last thing I want to talk to you about today is if a figure is a parallelogram, then its opposite angles will always be congruent. And we're going to do a proof of that in a second. So opposite angles are congruent if it's a parallelogram. Opposite angles are the angles that don't share a side. So here's the proof. Now, I didn't provide anything, so we're going to have to do this from scratch. What's the first thing we're going to put in here?
Given.
And given parallelogram A, B, C, D. So what does it mean when we have a parallelogram?
BC is congruent to AB and BA is
Not congruent.
Parallel.
Well, I mean, yeah, you could say congruent. You could actually say congruent. Remember, what I'm going for is to prove that these two angles are congruent.
Well, let's prove the lines parallel.
Yeah, so we'll say the line's parallel first. Shelby, what you were saying was not wrong, but it just doesn't apply to what's going on here. So we need to know that AD and BC are parallel, and we need to know that AB is parallel to CD. I don't know if I said that right. So it's BC is parallel to AD, AB parallel to CD. It's what's marked on the drawing. That would be the definition of what?
Parallelogram.
Yeah, that's just the definition of what a parallelogram is. Now, you could go in and put a statement in there that BC is congruent to AD and AB is congruent to CD, and that would be that theorem that we just proved. But we don't need it for this particular problem. That doesn't gain us anything. Knowing that all of the sides are congruent doesn't help us to prove that the angles are congruent. The next link in this is probably the trickiest. So this is one of those where you kind of have to know where you're going, and then you have to know what all the rules are that you can use, and then you find a rule that would fit to help you get where you're going. This is where knowing your note cards pays off. I'm pretty good at this stuff. I know that if I can prove that A is supplementary to B and C is supplementary to B, then I'll have two angles supplementary to the same angle, and that means something. So that's what I'm going to say. I'm going to say angle A and angle B are sup. Angle B and angle C are sup. And how can I say that? Consecutive angles in a parallelogram are sup. It's a pretty horrible view. And then once that I prove that both A and C are supplementary to B, I can now say that angle A is congruent to angle C because of the congruent supplements theorem. And if you remember, the congruent supplements theorem said if two angles were supplementary to the same or congruent angles, they're congruent to each other. Yes, ma'am?
Why couldn't you use alternate interior angles congruent?
What alternate interior angles do you see?
I don't know. That's just what came into my head when I thought of parallel lines, and then like A and C are.
So it's true, if you have parallel lines, you have alternate interior angles. Generally, they're not going to show up in a parallelogram unless you have the diagonal. And I don't have the diagonal drawn here, so I would have to construct that diagonal, and that's a little bit more work than I want to do for this proof. So basically, to answer your question, the reason I wouldn't use alternate interior angles isn't because they don't exist. It's because in this particular picture, A, B, C, and D are not any of those. However, A, B, C, and D are consecutive angles. They are same-side interior angles if you wanted to use that reasoning. So I could say that B was supplementary to C because same-side interior angles are congruent when lines are parallel. I could say A is supplementary to B because same-side interior angles are supplementary when lines are parallel. Technically, I didn't even have to put step 2 because I already know that based on that last theorem we looked at, I already know that consecutive angles in a parallelogram are supplementary. So I don't even need to mark anything parallel. I just need to know it's a parallelogram. But the book already had these things marked, so I thought I'd put the reason down there for them being marked that way. All right, so here's what I want you guys to do, and you can work with your partner. I want you to complete this proof. So in this proof, we are trying to prove that this angle and this angle are congruent. I'll give you a hint. It might be helpful to use an auxiliary drawing. And I'll give you probably about 7 or 8 minutes to do it. So hopefully you and your partner were able to complete the majority of this proof. So let's see where we'd have to go with this. This is something I would expect you to be able to do on a quiz or a test. I know this was a little bit difficult because there's a lot that goes on here. Like I said, an auxiliary drawing might have been very beneficial. So let's see what we would come up with. Yep. So that's a pretty good place to start. We'll start with the given. So the given is parallelogram A, B, C, D, and AK is congruent to MK. So this is the first indicator right here that I might need an auxiliary drawing because I can't actually mark AK congruent to MK because there's other stuff going on. So I think that's the first thing I'm going to do is I'm going to go ahead and make a little auxiliary triangle right here that would represent that. See if I can do that. You know what? Let's try actually doing it over the top of the triangle that's given. Close enough. So here's going to be my auxiliary drawing. Let me roll that up so it's not in the way. This is A, this is M, this is K, and I can go ahead and mark those two sides congruent. All right, so I got a lot of different directions I can go here. I can either expand on this information or I can expand on this information. Remember, the ultimate goal is to get this angle congruent to this angle. Where do you want to expand from here? Yeah. Go ahead. You don't? You have a question? Okay. I think I'm going to just expand on the, yes.
Well, I was trying to, the mid-segment theorem where BC would be congruent to AM. Can we use that?
If you can somehow prove that B and C are a midpoint, both midpoints, then you could.
That's what I was trying to do.
You can't.
I tried to prove that AB and all that were like congruent to each other, and I couldn't think of what I could call.
I think that that's a valid thought process to pursue. At some point, you should realize it's a dead end.
Yes. I mean, I did. I left it blank.
Right. So if you had gone down that road, I would probably give you some credit for exploring that, even though it wasn't valid in the end. That's fine. That's part of what you do with proofs is you explore. So that's one thing I've noticed here is that I have an isosceles triangle. So the isosceles triangle theorem is going to let me say that angle, so this is angle M, but really if you look at it in terms of the big picture, it's angle CMA. So angle CMA, I'm sorry.
I want it to be K.
Let's call it CMD.
Well, it's still the same thing.
It's still the same angle. The reason I'm choosing the letters that I'm choosing is because I am trying to be consistent with where they would show up again later in the proof. And so this angle has already been defined as CMD in another proof, in another statement within my proof. So I think I'm going to try to be consistent. However, angle A hasn't been defined anywhere, so I'm just going to call it angle A. And that was the what? Is it the isosceles triangle theorem or is it the converse? Who says converse?
Oh, Lord.
Who says isosceles triangle theorem? So isosceles triangle theorem is correct.
No.
It's not the converse. In the converse, you have the angles first and you get the sides. All right. So now we've got basically this angle congruent to this angle. What I'm going for is this angle congruent to that angle. So I think now I need to start talking about what a parallelogram is. Well, in a parallelogram, what do you know about opposite angles?
They are congruent.
Right. So I can say that angle A is congruent to angle BCD because in a parallelogram, opposite angles are congruent. And now I can say that angle CMD is congruent to angle BCD by what? If this is congruent to that, and that's congruent to that, how do I know that that is congruent to that?
Metric.
Close. Transitive.
Transitive. I was just flipping to those cards. I think.
And now I would go ahead and say angle BCD is congruent to angle CMD so that I match the proved statement exactly. And what lets me flop those around? That's symmetric. Which is cool because we haven't used a symmetric property yet in a proof. All right, so
It's me again,
long,
last one.
huh?
It's me again, last one.
Okay.
Spanner cable.
Okay. So, yeah, this is kind of a tough proof to do. And I might have gone off on some tangents, like I might have marked all of the things parallel by definition of a parallelogram. I might have tried to prove mid-segments and stuff like that, but this is still doable. This is something that I feel like you guys should be able to do on a test or a quiz. All right, here's the homework for tonight. Hope you enjoyed the lesson.